Now we're going to look at chemical bonding and the types of bonds that elements form. Since 1916, chemists have recognized that the noble gas elements are very stable. Electrons in the highest main energy shell are called valence electrons. These are outer shell electrons, and they play an important role in chemical bonding. For example, chlorine, highest main energy shell is N equals 3. There's a 3s and a 3p for a total of 7 valence electrons. Chlorine is in group 7a. Beryllium, valence shell is N equals 2, and there are 2 valence electrons for beryllium. Beryllium's in group 2a. Scandium is a transition metal. Highest occupied energy level is N equals 4, and there are 2 valence electrons for scandium. Scandium is in the B groups. So if you're in A group, the number of valence electrons is equal to the number of the A group. If you're in a B group, transition metals, for the most part you have 2 valence electrons. In some cases, chemical bonding results from the transfer of one or more electrons. This leads to the formation of ions and a bond type known as ionic. Metals and nonmetals tend to form ionic bonds. In other cases, chemical bonding results from a sharing of pairs of electrons. This leads to molecules with covalent bonds. Nonmetal compounds tend to form covalent bonds. The transfer or sharing of electrons occurs to the extent that each atom involved acquires a stable electron configuration, an octet of electrons, which is 8 valence electrons. Lewis dot symbols. The Lewis dot symbol consists of the chemical symbol surrounded by the valence electrons. For example, beryllium has 2 valence electrons, so the Lewis dot symbol would look like this. Nitrogen is in group 5a, so nitrogen has 5 valence electrons. We put 1 on each side, and the 5th one we can pair up on any of the sides. So there's the Lewis dot symbol for nitrogen. Chlorine is in group 7a, so it has 7 valence electrons. The most you could have on a Lewis dot symbol would be 8, and those would be the noble gases. An ionic bond results from the transfer of one or more electrons from a metal to a nonmetal. You get ions, a positively charged ion, a cation, and a negatively charged ion, and an anion, and there's an attraction between positive and negative, resulting in an ionic bond. In the solid state, each ion surrounds itself with ions of the opposite charge, and this produces a crystal. We will look at crystalline solids a little bit later. But let's consider the compound formed between sodium and chlorine. Well, sodium is a metal. Metals tend to lose electrons. So we're going to lose the 3s1 electron from sodium. Chlorine, electron configuration of 3s2, 3p5, it's going to gain 1 to become 3p6. And so sodium and chlorine combine in a 1-to-1 ratio in NaCl. Na plus is isoelectronic with neon. It has the same number of electrons as neon, which is 10. Chlorine is isoelectronic with argon. Argon has 18 electrons. Now consider the compound formed between calcium and chlorine. Well, calcium ends in 4s2, so metals are going to lose. Calcium is going to lose 2 valence electrons. Chlorine, again, is going to gain 1 to give it 3p6. Calcium and chlorine are going to combine in a 1-to-2 ratio, 1 calcium to 2 chlorine. Calcium is going to be isoelectronic with argon. Chlorine is going to be isoelectronic with argon. So the ions have very stable electron configurations because they're isoelectronic with the noble gases. Let's look at one more example. Magnesium and nitrogen. Well, magnesium is going to lose 2 valence electrons. So magnesium will be isoelectronic with neon. Nitrogen is going to gain, in this case it needs to gain 3 to become 2p6. The ratio that these are going to react in is a 3:2 ratio, so Mg3N2. Now to get the ratio, you can either draw out the valence electrons and transfer them, or we can do it this way. Magnesium is going to form a 2+ charge as it loses 2 electrons. Nitrogen is going to form a 3- charge as it gains 3 electrons. We can cross the charges to give us the formula of the balanced compound, Mg3N2. So you can either draw out the valence electrons like this, or simply cross charges for the metal and the nonmetal. When hydrogen combines with chlorine, the difference in electronegativity is small, and neither atom tends to give up an electron. So the bonding between hydrogen and chlorine involves the sharing of electrons. So chlorine has 7 valence, and hydrogen has 1. This is a shared pair of electrons between the hydrogen and the chlorine, a covalent bond. So each atom in HCl is able to attain a noble gas electron configuration. Sometimes a covalent bond is represented by a dash instead of 2 dots. So for HCl, we could write it like this. Nitrogen forms a triple bond, so nitrogen could be represented with 3 dashes for the triple bond. When we write Lewis structures for covalent compounds, here are some useful guidelines. Number 1, all the valence electrons have to be represented. Number 2, ordinarily, each atom acquires an electron configuration with 8 electrons, except hydrogen only wants 2. Number 3, all electrons in a Lewis structure are paired normally. We don't have single electrons floating around. Number 4, most often both atoms in a bonded pair contribute 1 electron apiece to the covalent bond, but sometimes both electrons are derived from a single atom. For example, SO2, the Lewis structure looks like this. This right here is called a coordinate covalent bond. Know that term, coordinate covalent bond. Both electrons in that bond come from sulfur. Number 5, sometimes you have to represent double or triple bonds. Rule of thumb for me, I always try single bonds, and if single bonds don't work, then you try double or triple. And then number 6, sometimes it's not possible to draw a single Lewis structure that's consistent, and so sometimes we have to represent the structure as a composite or hybrid of 2 or more plausible structures.